Humanity's greatest strength has always been our ability to learn, adapt, and manipulate our environment. However, this manipulation, like everything, comes at a price. Every action we take, every machine that moves, every light we turn on has a price, and this all relies on energy. However, physics has rules, and one rule governs all of this. The second law of thermodynamics. Energy transformation increases entropy, the universe's natural drift towards disorder. On that scale, that disorder looks like pollution, heat, toxins, waste. Entropy isn't just a law, it's a problem we must solve. So the question becomes, how do we power the future without unraveling it? Let's start on what we know. First, let's look at hydroelectric and wind energy. Hydropower and wind energy harness motion, the kinetic energy of the Earth's fluids. Hydroelectricity uses gravitational potential. Water held in a reservoir behind a dam has potential energy due to its height. When it's released, gravity accelerates the water, converting potential energy into kinetic energy, which then spins a turbine shaft. Inside a turbine's housing, there's a rotor that spins within a stator, which is a ring of magnets and copper coils. Thanks to Faraday's law of induction, the changing magnetic field induces an electric current. Wind turbines utilize the same principle, but the blades catch the moving air. The blades shape pressure differences, like airplane wings, driving rotation even at low wind speeds. However, there are some limitations. Wind and water aren't always available. Turbines could also induce mechanical wear, and thus entropy creeps in through maintenance and efficiency losses. And dams, while clean, disrupt ecosystems, flood lands, and release methane from decomposing organic material. Next, let's look at another very popular form of energy that is both sustainable and also very reliable and is gaining a lot of prominent use as of recent years. Solar energy. So let's start from the very beginning. Sunlight is pure energy. Solar panels use it directly through the photoelectric effect. While the photoelectric effect does deal with some quantized events, I will try explaining it in the most basic way possible. However, this may induce some mistakes due to a very broad oversimplification. So the photoelectric effect occurs when photons strike certain materials, like doped silicon, for example. This in turn transfers energy to electrons. If the energy then exceeds the material's work function, electrons are freed from the atoms, creating a flow. This panel is structured with a p-n junction, which is a boundary between positive and negative semiconductors. Freed electrons move across this junction, creating a direct current, or DC. An inverter is then used to convert this into alternating current, also known as AC, compatible with the grid. So there are some challenges. For example, intermittent generation. Sunlight varies with weather and time, meaning that the power collected from the sun is variable. As of currently, storage is also still very expensive and inefficient. And production of panels also requires rare materials and produces waste. Again, entropy in the system. However, at this current point, solar remains the most modular and scalable source, which is why we are seeing a lot of widespread use of it right now in the modern day. Next, let's look at geothermal energy. Deep underground, the Earth's core radiates a heat left over from planetary formation and radioactive decay. In volcanic regions, this heat is accessible. Geothermal power plants drill down to tap this energy and use it to generate steam. And there are two types of these main types of geothermal power that exists. Flash steam plants, which bring up superheated water, which then flashes into steam, or binary cycle plants, which use a secondary fluid with a low boiling point, allowing for the use of lower temperature heat. So what applications does this have? Geothermal energy best works near tectonic boundaries, such as Iceland, Japan, and parts of the US, and it's also very, very good for direct heating of homes, greenhouses, and industry. It's clean, however, it's geographically limited, and drilling causes seismic and water contamination risks, making it a little bit more risky and more situational. Finally, let's go into the most interesting form of energy, in my opinion, which is nuclear energy. So, as stated previously, the most contentious energy source, as in the modern day, is nuclear energy. And at the heart of nuclear fission is Einstein's equation, infamous equation, E is equal to mc squared. Fission is a process in which heavy nuclei, such as uranium-235, are split. So in this process, a neutron strikes the nucleus, which becomes unstable and splits, releasing energy, mostly as kinetic energy of the fragments, which turns into heat, and more neutrons, which can trigger further fusions, forming what we know as a chain reaction. This heat boils water, drives steam, spins turbines, and generates electricity, just like fossil fuels, however, with no carbon emissions. So, in terms of some physics advantages, the energy density of this form of energy generation is millions of times higher than chemical fuels. And just for reference, 1 kilogram of uranium can generate as much as millions of energy. Wait, sorry. 1 kilogram of uranium can generate as much energy as millions of kilograms of coal. However, this comes with many different challenges. Radioactive waste is a very huge byproduct with long half-lives, and they must be stored safely for thousands of years, which is obviously not sustainable due to very volatile changes in government structures. Nuclear accidents, mostly due to the design flaws or natural disasters. Think sort of like Fukushima back in like 2011, or even Chernobyl. When these plants are not properly monitored, it could cause for there to be a lot of destruction, which is why we need to be investing in in these sorts of energy. However, we need to monitor that it's actually kept up to big and very safe safety standards. However, with this, new reactor designs such as SMRs, which are small modular reactors, and molten salt reactors offer passive safety, less waste, and resistance to meltdown. And there's also, as of lately, discussions about fusion, which is the opposite of fission. So, for example, fusion would involve combining light nuclei, like hydrogen isotopes, into helium, and this would release even more energy, no long-lived waste, and no meltdown risk. The biggest hurdle, achieving net positive energy. We're close, however, we're not there yet. Nuclear remains the only scalable, constant, low-emission baseload power available today. Every energy source, however, does carry physical trade-offs as of currently. We have efficiency losses, entropy losses, infrastructure needs, and environmental footprint. However, clearly, there are some more manageable than others. Hydro, wind, and solar are vital, but intermittent. Geothermal is clean, however limited due to its situation and its position and its reliance on actual geographic positioning. However, nuclear is constant, but politically volatile. The truth in all of this, there is no single solution. However, a hybrid system integrating renewables and modern-day nuclear might be our best chance. While we can't escape entropy, we can choose how we create it and how much. This energy transition into the new world isn't just technical, it's also philosophical. Can we truly embrace complex solutions over our convenient fears? Can we see nuclear energy as not as a threat, but as a tool? Because if we want a clean, livable future, we'll need all the tools we can get. Thank you. This is Adolfo Malabanan signing out.